The purpose of today's video is to allow you to learn the last two properties from the periodic table. The properties that we're looking at today are the successive ionization energy and the electron affinity. The biggest difference between these properties and the properties that we have covered previously are that we are focusing more on group trends this time, meaning a group at a time instead of individual elements, in order to predict these properties. The first one that we're looking at is the successive ionization energy. And a successive ionization energy is just the energy required to remove another electron from an atom that is already positively charged. So the amount of energy required to remove the next electron from a cation. One type of successive ionization energy would be the second ionization energy. And the second ionization energy is the energy required to remove the second electron from a +1 cation. We could also talk about the third or the fourth or the fifth, really the whole way up to the 8th ionization energy. Each of these ionization energies that has a number in front of it like this, each of them is a type of successive ionization. So if we're looking at our Bohr model of silicon here, right now it's neutral silicon. If we want to remove the first electron from silicon to create a +1 ion, that's going to require energy. And the energy required to do that was the ionization energy we learned about in the last section. Today, we're talking about removing a second electron from the silicon +1. When we do that, we need to put in more energy, and we create silicon +2. Now, if we're looking at an individual element, the second ionization energy is always going to be bigger than the first. The third will always be bigger than the second. The fourth will always be bigger than the third. The more electrons you remove, the stronger the protons are going to pool on the remaining electrons. So it's always going to take a little bit more energy than it did the prior one. But that's actually not what we're going to be comparing. Instead of comparing the amount of energy to create silicon +2, the second ionization energy, with the amount of energy to create silicon +3, which by the way would be called the third ionization energy because we took the third electron away from something that was already +2. Instead of comparing each of these for silicon, we're going to be comparing the ionization energies for different elements within the same period though. So before we do this, let's just quickly remind you, a low ionization energy means that it's easy to remove the electron. That electron isn't being held on as tightly. A high ionization energy means it's hard to remove that electron. It takes a lot more energy because the electron is being pulled on harder. We're going to compare magnesium to aluminum, and we're going to say when do they have lower ionization energies and when do they have higher ionization energies in comparison to each other and the other elements within that period. So if we start with neutral magnesium, we have 12 protons, we have 12 electrons. Honestly, neutral magnesium, he's kind of like meh. He's not stable, he doesn't have a full valence shell, but he's slightly more stable than something that only has one valence electron, so really meh. If we look at the ionization energy initially to create magnesium +1, it doesn't really help him out that much. He's still not stable. But if we put in just a little bit more energy to create magnesium +2, now that entire ring goes away, which means he now has 8 valence electrons, which means he's now happy. Because +2 is the common charge, +2 is the number of electrons we need to remove in order to make him stable, +2 is where magnesium is going to have the lowest ionization energy compared to other elements in its period. So elements in group 2, like magnesium, we say they have a low second ionization energy. They have a low second ionization energy because removing the second electron makes a +2 charge, which makes them stable. Similarly, if we look at aluminum, aluminum starts with 13 protons, 13 electrons. If we look at the initial ionization energy, it really doesn't do much. If we look at the second ionization energy, still not great. But if we look at the third ionization energy, taking that third electron away is going to remove the entire valence shell, which will give aluminum its +3 charge, which again is its common charge. And it's its common charge because that's the charge that's going to make it stable. Since removing the third electron made magnesium stable, it's not going to be requiring much energy to do that. It wants to lose the third electron. So elements in group 13, like aluminum, they're going to have a low third ionization energy when we compare them to the other elements within their period. High ionization energy, remember, means that it's hard to remove the electron. It's going to be incredibly hard to remove an electron from an atom that's already happy, an atom that's already stable, because you're taking something that's already stable and making it less stable. You can also think of it in terms of you're taking something that is now a whole energy level closer, getting pulled on by the protons even harder. It's going to require a lot of energy to do that. So if an element like magnesium has a low second ionization energy, it's going to have an incredibly high third ionization energy. Taking another electron away from something that's already stable is going to make it incredibly upset. And if you're doing that, you're going to have to give it a lot of energy for it to be willing to lose that third. Over here, aluminum had a low third because that's what made it stable. But if you try to take the fourth electron away, now you're making it less stable. Now you're making it upset. That's going to take a lot of energy. So if we go back to our original example of silicon, we had talked about silicon +3, the third ionization energy. If we remove one more electron from silicon, that takes away that entire energy level. It's now stable, so it would have a low fourth ionization energy. That's what made it stable. But if we try to take another electron away after that, that's going to make it less stable. So silicon would have a high fifth ionization energy. And I'm hoping that looking at magnesium, aluminum, and silicon allows you to kind of think in terms of what that looks like on the entire periodic table. If we compare the successive ionization energies for elements that are within a period, so within a row, we will find that the lowest ionization energy will occur when an atom is losing its last valence electron. That's because that's what makes it stable. And the highest ionization energy will occur if you try to take another electron away after that one. So think about our periodic table and think about the number of valence electrons that are in each group. Group 1 had 1, Group 2 had 2. The D block we're going to skip over. We're not going to worry about the transition metals at this point. Group 13 had 3, 14 had 4, 15 had 5, 16 had 6, 17 had 7, and finally the noble gases had 8 valence electrons. In order to figure out where the lows occur, we really just have to match number. So, Group 1 had the low first ionization energy. It was really easy to take the first electron away from them. Group 2 will have the second, low second ionization. Group 13 will have the low third. Group 14 will have the low fourth. Group 15, 16, 17, and 18. All of them will match up. The number of valence electrons tells you when they will have the lower ionization energy in comparison to the other elements within the period. Remember, taking that number of electrons away takes it back to a stable energy level. It takes it back to a ring that already has 8 electrons. If you try to take another one away after that, that's when it becomes incredibly hard. So, something that has a low first is going to have a high second. Low second would be a high third, fourth,